So now after talking about the properties of waves and doing the Slinky Lab and doing all that stuff, do we have some different things we want to add to this concept now?
No.
Nothing at all. Cody, okay? Or Clay, sorry.
What?
Nothing we want to add here.
Actually, nothing.
Not like we learned anything more from the last time.
You don't think so?
Other than like the class, but like since that class.
Yeah. Well, this is at the start class. So right here we've got different types. You did very well with the different types. What about the properties though? Frequency, speed, we talked about that. I know we talked about all this stuff too. Amplitude, frequency, wavelength, stress.
What was like the type?
Nothing
like
cool.
Longitudinal wave and stuff.
What's that?
The longitudinal wave and stuff.
Hey, there we go. So there's types of waves. I'll put that down here. We've got transverse. And longitudinal. Yeah, right.
It doesn't like carry things, like just doesn't push things away. A wave is a disturbance that carries energy from place to place. Like we talked about like the depth and how it would sit on the wave if there was no other force acting upon it.
Absolutely. Did everybody hear Ryan? Are there?
Yes.
Okay. People in the back, you might not have heard, but basically what she said is that waves don't necessarily carry material. So she used the example. If you've got a rubber ducky on the wave is just going to make it bob up and down. It doesn't actually bring that material along with it. So I'm just going to say that's a property. I'm going to say it doesn't carry material. Okay?
Should we have this mapped down?
I don't think so. I think this is just like a class. And if you want to, then go for it. Yeah?
There's the compression and refraction part of the
Stop copying off your notes.
the longitudinal waves, I think, is the one.
Okay, I'm going to finish writing this. I didn't hear that at all, so I'm going to, it does not
Yeah, don't copy.
carry.
Your mumble.
So, what was that?
The compression and refraction.
Right, okay, so you're talking about the different waves that we talked about the waves. So there's compressions and refractions. I'll just go here.
I barely remember Saturday.
I'm just going to write conc for compression. Conc. There we go. So just the different ways we describe them. Yes, Alex.
Like we talked about how the end, like when on that website thing, when the end is open or like held or like loose, it like made the wave different and like it came back differently, or else it didn't come back at all.
Awesome, right. So the properties change based on if it's an opened or fixed end.
Yes.
How that wave will reflect.
Yeah.
So I'll just say down here, open versus fixed end. Okay, awesome. This is good. This is really good. Anything else that you took away from the lab, or anything? Could be anything about waves, how we describe waves, what waves do, the definition of waves. Ryan, I kind of talked about that. Yeah.
One full wave is either crest to crest or trough to trough.
Right.
Trough.
Trough, yeah. That's perfect. I'm going to put that right up here. I'm going to say, what do we want me to say? Wavelength is crest to crest, I'm going to say. Okay, this is going to blow your minds. Instead of writing wavelength, I've got a little Greek symbol that I use, okay?
WL.
No. Right there. This
I don't like
means
it.
wavelength,
I don't like it.
okay? I don't know why. I don't know why. It's an upside down Y. It's not actually what I think it's called. It's not lambda, is it? I can't remember. But you know what it is. But I'll figure out what it's actually called, and I'll tell you. But this is the symbol for wavelength. So wavelength is crest to crest.
Let's try to the bottom of all this.
Crest or trough to trough. So I'll just put dots. Crest to crest, trough to trough. Anything else we want to? Do we want to change any of the stuff we said? We said invisible. Are waves invisible? Yeah.
It is lambda.
It is
Yeah, I
lambda?
just googled it because I wasn't sure. I didn't
Awesome. So this is
kind of
called
on
lambda.
the side.
Are waves invisible?
No.
Depends.
Not all
Yeah.
of them.
Yeah, we could say
See
not
how many
all.
waves are
They
visible.
I can see a water wave. But I can't
the
see a
medium.
sound
We
wave.
see the medium they travel through. So if it's an ocean and we're looking at the water, we don't actually we see the waves, but we're just looking at the water. We see how it's carrying the material, right? So yeah, we see the energy and the displacement of energy is what we see. Okay. Anything else we want to add to this, or should we keep on rocking and rolling? Okay, awesome. My request of you, or my proposition, is that we're going to talk about how waves travel through different materials. Okay? So I want you, just at your table, to come up with an explanation or a hypothesis of what do waves travel the fastest through? Does it travel fast through gases or solids? Okay, we kind of talked about it right at the end of class on Thursday, and we didn't really get an answer. So I want you to try to come up with an answer. You can use your phones and look things up. You can use the computers on the side if you really want. But we're going to give just you and your table about 5 minutes to try to answer that question. Let's say, would a wave travel faster through the air, or would it travel faster through water? Okay. Does everybody understand the little assignment? Awesome.
True. Okay, guys, well, you're wrong. It travels faster than light.
Now why don't they put satellites in the water?
You build a space station on the water. You build a water station. What? That one right in if you want to hear it out the other. I'm still over here like.
It was on Netflix. It was kind of cool to see how bad it was.
Yeah, I wasn't sure if you thought the loading up of the teacher was cool or.
Cody's like.
Was it Discovery, like the?
It was on Netflix.
Yeah, no, but what was the name of the? Or was it actual? Sorry?
Challenger. Discovery exploded too. Yeah, it just sucks at building space stations.
Bet your $100 or I think this site has
I think we should go with that.
Yeah.
Even though
Yeah.
you grew up in the back.
So you're telling me we're on the same football team and anyone he talks to can talk to you.
You probably did.
Who's the only defense? Who's really good at it? Drafted, got drafted higher than Corbin, actually. Is that what it paid him? Yeah.
Well, electromagnetic.
I heard he went first overall.
Yeah.
Yeah.
He said electronic waves move fastest through gases, and then sound travels fastest through solids. So this answer isn't definite.
Right. Okay. We'll talk about that. We'll talk about that.
You think about it when you use like amplifiers.
gonna ask the other one. Because I like your answer, but you were gonna problem too, so I'm gonna keep it simple and then I'm gonna get to yours. Okay, so which table has a hypothesis or an idea? Jacqueline, I saw your hand first. So all because molecules are close together. Okay, awesome. You're gonna get some, you too? Okay, awesome. Ryan, yeah?
I have a question.
Yes.
If it travels faster in solid, how come they don't put satellites in rocks?
How come they don't put satellites in? Because it has to, like,
Spread
it's
across
traveling
the
through
whole
air the
world.
whole time. It's not traveling through rock the whole time. You know what I mean? Like, well, where are you getting this?
Well,
Do you know what I'm
Wouldn't
saying? Like,
yeah, but
just because the satellite's in the rocks, it still has to travel through air that entire time to get to the rocks and the satellite. Like if we were talking like a radio
Yeah.
wave.
Genius, Cody.
shut up, Alex.
But
Great.
I'm trying to think of some technology they use where they actually use that.
Yeah, Cody, you kind of.
If you
Yeah,
think like of
that's great.
acoustics or something like that,
Yeah.
you want sound to be the loudest. So that's why some places like your bathroom would have the best acoustics because it's like a smaller place and then it would bounce off of each other because it's hard surfaces. So
Yeah.
your sound would bounce off each other, making it louder and amplified more.
Yeah.
Acoustic.
So what Rihanna told me was the answer's not definite, or the answer's not definitive, because she brought in something called electromagnetic waves. Okay? And Carter, Brad, I'll just get your attention up here. To me and Dane. Thank you very much. Okay, awesome. So what Rihanna said was that, well, electromagnetic waves travel faster through air, I believe is what she said. So there's two types of waves that we
Gases.
haven't discussed yet. There's mechanical waves, and that's everything we've talked about so far. The second is electromagnetic waves, which is basically just some of these. So like microwaves, radio waves, sound waves, and those types of things don't necessarily need a medium to travel through. So they look a little bit different. But we're going to talk about those when we talk about light, and we'll talk about all that. But right now, what we're focused on is mechanical waves, okay? And I'll just give you a visual of what that looks like, why they travel faster through a solid. So if we have something like this, what did you say, Jacqueline? The particles are closer together? Yeah, particles, molecules, they're all closer together. So
Do you want to film this?
yeah, I think it is filming, isn't it?
No.